kind introduction. So I'm going to start my talk on quinoa. Title is Quinoa Promising Plant for Healthy Eating. This is mostly in collaboration with my former student, Dr. Guandian Li. He is now a academic in Chinese Academy of Sciences, China. Can you show me the slide? So let's continue. So a few of you may have already seen my slides as I gave a lecture to a class of students yesterday afternoon. So this is a book I published at the beginning of this year. It's specifically about the quinoa and the crop and the chemistry and the technology. And of course, also a lot of information about nutrition. It's published with the academic press imprint of the elsewhere. So if you are really into this crop later, you are certainly welcome to find out this book. The outline of my talk is on these slides. Firstly, a bit of an intro, and then talk about a range of different types of properties. In particular, we'll talk about this major component of quinoa crop, which is the starch. And finally, I'm going to give us a little bit of perspectives in the future work. The quinoa is a crop originated from the South American and the Andes. It is so important that the United Nations in 2013 designated that year as the International Year of Quinoa. A lot of activities were conducted on that specific year, and it has been carried on up to this day. It is such an interesting crop that is NASA, the American Agency for Space Program, think this crop can be used for this long-term long duration manned space flight. So I'm going to play you a little bit of video showing you how this crop can play a role in this space program. So video shows you how quinoa can play a role in this space program. There are already a number of commercial products quinoa available from the market. For example, those were found in the New Zealand market, in the supermarkets there. So those are quinoa-based products, food products that can be found in Chinese market. The quinoa is a pseudo cereal, so it is botanically not belonging to the Poaceae family. The cereals such as rice, wheat, they are part of the Poaceae family, but quinoa is not. Nevertheless, they have a lot of similarity in the application and the processing. There are different varieties of quinoa with different colors, black, white, and the cultivation is scattered around different places, sea coastline, coastal region, up to really high altitudes. So this is a field, a quinoa growing, and you can see this background of snow mountains, which denotes the high altitude. In South America, the quinoa was a major crop for Incas for a very long time. It has a significant religious meaning to the Incas. In the 16th century, the Spanish came to South America and conquered the land. As a consequence, they banned the growing of quinoa because quinoa has such a culture and religious significance for the local Inca people. Up to the present date, during the last 2 decades, there's a renewed interest in quinoa consumption for different reasons. For example, nutritionally, quinoa is considered a balanced crop food. Environmentally, it has a very high feasibility to grow in different types of climate and environment. As a result of this, it has been spread all across the globe. For example, in China, that's where I'm from, we grow quinoa now, in particular in those provinces with harsh climate, such as this orange-colored place, Qinghai province, where the altitude is really high. It is part of this Qinghai, Tibet plateau. The altitude can be over 4,000 meters, and it can grow quinoa there, but it cannot grow many other crops such as rice. The nutritional or functional properties of quinoa, there are many different aspects. I'm going to talk a little bit about some of the aspects. It has its gluten-free nature. Gluten-free, so nowadays a lot of people got this gluten intolerance and a celiac disease because they can't eat some of the major crops, such as wheat. For those people, you can use quinoa as a substitute for their energy intake. So it has this background that also some people think gluten-free products are healthier. even though they are not really gluten intolerant or having any celiac diseases. For the nutritional composition, it is considered a complete food. In one very particular aspect is this amino acid, essential amino acid composition. In comparison with some other major crops such as rice, which is a staple here in Indonesia, the rice is lacking this lysine, which is a type of essential amino acid. But the quinoa has not this problem. So it is considered a complete food. As a result, the FAO listed as a very promising crop for food security and human nutrition. Food security means we have this climate change across the globe, rising sea level, harsh climate, increasing saltiness of the land, even in Indonesia. We have this sea surrounding us here. So this quinoa can grow if you can't grow, for example, rice, because the land becomes too much containing salt. In terms of the mineral composition, quinoa stands out again in comparison. In some of the mineral, the seeds, for example, can be high, rich in potassium, and also the leaves, the quinoa leaves can be eatable. So it is particularly high in calcium. In terms of the lipids, nowadays we talk about the lipids, the unsaturated fatty acids and the saturated fatty acids. It is commonly believed that if you want to live longer, you tend to eat more unsaturated fatty acids. And in this regards, quinoa lipids is rich in those unsaturated fatty acids, including monounsaturated fatty acids and also polyunsaturated fatty acids. In terms of these polyphenols are nowadays considered dietary antioxidants. It can help you to maintain health, anti-aging property, for example. Quinoa, again, contains some of those phenolic acids as shown in this table. Malic acid, gallic acid, dehydrogenolic acid in the whole grain form. In contrast, rice, for example, does not have those higher concentration of these phenolic acids. Saponin is there is a type of glucosides as shown this figure on the right side of this slide. One negative aspect of these saponins is that it tastes bitter. So people who eat quinoa, they found out that maybe too bitter for them. That is partially because of the saponin. You can, of course, get rid of the saponin by either wash it out through processing or create a new variety that has very little saponin. In the market, there was already variety containing little saponin. And another aspects of this, another side of this coin is saponin can be biologically active. For example, it has this anti-cancer property. The other similar functional component is tannins. There is a oligomers for flavin-3 oil units. It also tastes bitter and astringent. It is mostly concentrated in the outer layer of the quinoa seeds, so you can get rid of it by milling, for example. But on the other hand, it is biologically active. It is considered a type of antioxidants. So this slide is a summarization of what we have talked about in terms of the nutritional composition. Slides showing you here the nutritional approximate composition of the quinoa seeds. So if you take a look at these figures, you find out that the major component is starch, amounting up to 55% on the weight basis. And if you transfer it to, convert it to dry basis, it will be over 60 or even 70% of the dry weight. We also have some other components such as dietary fiber. For quinoa, the dietary fiber components is more similar to fruits and vegetables rather than to cereals such as wheat and rice. So you can find pectin as a component of dietary fiber in quinoa. Because of the high concentration of starch, we want to study a little bit about starch more. And from this diagram of the anatomy of the quinoa seeds, we see these different parts of the quinoa seeds as shown on the left side of this diagram. The perisperm contains a significant amount of starch. Because it is a major component, we did a lot of work on them, and we extracted the starch from them. And we want to analyze the structure and also analyze the property, and also has many industrial applications. There are two types of starch molecules: amylose, which is linear, and amylopectin, which is branched. Is smaller, and amylopectin is larger. The two molecules, amylose and amylopectin, they interact with each other to form a granular shape, as shown on the right-hand side of this slide. And within this granular form, there are different levels of structure units or organization. You have the crystalline layer, you have the amorphous shell, and you also have the blocklet structure. The blocklet structure can be further zoomed in to have two layers of lamella structure, amorphous lamella and crystalline lamella. So at this level, the size has already become really small. For example, one layer of crystalline plus one layer of amorphous lamella is about 9 nanometers. So it's really small. So for cooking purpose, we want to destroy this lamella structure, especially the crystalline lamella. Destroy that 9 nanometer structure. If you take a look at the granule structure under the microscope, as shown on the right-hand side of this slide, you find out they are pretty small. The granule shape is about 1 to 2 micrometer. Because it's a major component of quinoa, so if you want to create quinoa products, or if you want to relate the nutritional property of quinoa, you have to find out the properties of a starch, because it's 90% of the total seeds weight. One in special aspects is that the granule size of quinoa is really small. It's only 1 to 2 micrometer. And the other starch from other major cereals, such as potatoes, such as wheat, are much larger. And the rice also much larger. We have analyzed a range of different properties of quinoa starch using various types of instrument. For example, in this one, it is called differential scanning calorimetric methods. It measures the heat. When you heat it up, when you cook it, you want to cook it, and the starch or the rice or the quinoa absorb a lot of energy. So you can actually quantify the energy. How much energy you have to input to destroy the structure and to cook it properly so you can eat it. Similarly, you can measure the heat absorption and heat releasing also as well. So how much heat has been released, how much heat has been absorbed by the sample. You can use this heat flow diagram. So here is a typical diagram showing you the analytical aspect of this technique. On the right-hand side, it is the melting of the quinoa starch, or it's about the cooking of quinoa. How much energy you have to put to cook it, you can quantify it. So we have maybe 7 curves there, and these 7 curves represent different types of quinoa varieties. As we just mentioned in the beginning, that red quinoa, black quinoa, white quinoa, etc. So those represent different types of quinoa. You found out there are variations between them, even though they're all quinoa, but they are different in their cooking behavior. So if the peak is larger, which means you have to put a lot of heat to cook it thoroughly. Also, the x-axis is the temperature. If the peak occurs at a lower temperature range on the left-hand side, which means you only need to heat it up at that lower temperature range to be able to cook it. The y-axis is the heat flow, how much heat you have to input to thoroughly cook it. So this is the DSC analysis. So it's not only you apply it in quinoa, you can also apply it in many other areas, such as other nutrients, lipids, for example. You can also measure the lipids because, for example, the lipids, chocolate. So at the room temperature, the chocolate is solid, but when you put it in your mouth, it starts to melt. So this melting process is the melting of lipids mostly. So you can measure the melting point of the lipids as well. Also protein. When we cook some food, protein-rich food, you cook it, you heat it up, it denatures. You can actually use this technique to analyze the denaturation of the protein as well. We made a comparison, the quinoa compared to many other crops or cereals. It has a lower cooking temperature, or so-called gelatinization temperature, which means it is easier to cook compared to, for example, cassava, compared to rice, which is easier to cook. Next slide. Another aspect of this is the viscosity. For example, when you cook rice, some of the rice are really sticky, some of the rice are not sticky. Like those basmati rice, the Indians like basmati rice. Those rice are not sticky at all. In comparison, the rice here tends to be much more stickier. So it is also, you make porridge. You make porridge, the porridge, you add a lot of water, the porridge become diluted. So that is related to the viscosity, and you can measure the viscosity using the instrument displayed here. For example, the first one is the rheometer. Next slide. So we measure the viscosity of the quinoa starch, different types of quinoa starch again. So on the right-hand side is the viscosity diagram. The y-axis is the viscosity, and the x-axis is the time. You add a little bit of water and mix it with quinoa starch. You heat it up, and you record the viscosity changes. So you have the increase in the viscosity after 10 minutes because you cook it up. Again, we see a variation in different types of quinoa in their pasting properties. Some of them have higher viscosity, some of them have a low viscosity, even though they're at the same concentration. The implication is if you want to make a thick soup, you choose those with a high viscosity. If you want to make a thin soup, you choose those with a low viscosity. So that's the implication for cooking. Also for mouthfeel, the quinoa has a unique mouthfeel. Of course, this unique means in comparison with other types of cereals such as rice or wheat. Another aspect is the swelling. It's just like when you cook the rice, you put water inside the rice, you cook it up, then the water will get absorbed by the rice. The rice granules will become bigger and bigger, swelling process. It's the same for quinoa. We also have the swelling. Related to swelling is the water solubility. When you make porridge, you cook rice in a lot of water, and they heat it up, and then the rice component will get solubilized in the water if you make a really thin rice porridge for breakfast. So it's a similar concept here. When you cook the quinoa in the rice, some of the component of quinoa get solubilized. So the diagram on the right-hand side of this slide is the relationship between these two parameters. On the y-axis, we have the swelling in the form of swelling power. On the x-axis is the water soluble index of water solubility. You find the relationship between them in a near linear relationship. The general conclusion from this experiment that it has a good water binding capacity at a higher temperature. So this is an illustration of what we just talked about, the quinoa and also what will happen to the starch granules on the granule level and also on the molecular level. What happens to the molecules? After you cook it, you pull it down, and sometimes you cook too much, you put them in the fridge. And then next day, the food becomes hard. So that's because the so-called retrogradation. So quinoa, if the higher retrogradation, then you tend to have a really firm texture after the overnight storage in the fridge. Quinoa has a slow retrogradation. For the food products, we want to know the texture. How do we measure the texture? When you eat food, some of them are really hard, some of them are really soft, some of them are chewy, some of them are slippery. So you can use this so-called texture analyzer to measure them. You put your samples in between these plates, and then you push it down. The force will be recorded accurately. In this way, you obtain the hardness, adhesiveness, and cohesiveness, a range of parameters. This is on the right-hand side of the slides is a typical texture analysis diagram obtained on quinoa. Here are some specific values. In comparison with others, those hardness, for example, tends to be low because cooked quinoa tends to be soft because of the slow retrogradation process. And you push down the probe in the previous slides twice to mimic the mouse biting. You bite them, and then you have, for many foods, you have to chew them many times. Just bite them once is not enough. You have to chew them twice or even many times, a couple of times, to break down the texture of the food. So here we did twice, try to mimic the eating process, oral processing process. Another important nutrition aspect is the digestion. So on the right-hand side, there's a glucose release curve. So the y-axis is the amount of glucose released when you digest the starch, and the x-axis is related to the time. We have, again, 7 different quinoa varieties. When you eat food, for example, when you eat rice or piece of bread, it will enter your mouth first, then it will enter your stomach, and then small intestine, large intestine. So there are a range of enzymes inside your body, such as amylase from the pancreas, from the saliva. So these amylases will break down the starch to release glucose, and your body will absorb glucose. Then you have the glucose in your blood. The glucose in your blood will be finally transformed into ATP for your daily activity. If you have really fast glucose release, it is not so good for people with diabetes. So for people with diabetes, you have to give them food that has a really slow glucose releasing behavior. Don't release the glucose so fast. So for this, from this experiment, we found out that some of the quinoa starch release glucose faster than the others. So the implication is that nutritionally, you may want to choose the suitable quinoa variety in order to create some diet for people with different conditions. If it's healthy people, it is okay to give them any type of quinoa variety. If it's people with diabetes or people who want to be healthy, live healthier, live a healthy life. So you may want to consider give them the variety with a bit less or slower glucose releasing property. Next slide, please. The freeze-thaw stability is related to the fridge. So when you buy food from the supermarket, some of them are frozen food. So you take them out from the freezer from the supermarket and you put them in your car and take them home. So this creates a temperature fluctuation. In the freezer, in the supermarket, it's -18. In the supermarket, maybe it's 20 degrees, 25. And then you take it out into your car. It's really hot outside, over 30 degrees. So there's this thawing in process. And then when you reach home, you put them back in the freezer in your fridge. Then it's again a freezing process. So you have these freeze-thaw cycles. For food products, you want to have the stability. Even though you have these freeze-thaw cycles, you still want to have the quality remained. So if you have really stable or high freeze-thaw stability, then it is good for this type of food products. When we measure the freeze-thaw stability of quinoa, we made a comparison between wheat and the barley. We found out that it has a higher freeze-thaw stability. So this is the implication for those frozen food. And finally, I would like to make a few speculations on the future research. There are many different types of processing. For nutritional application, you may want to use other processing techniques. For example, non-thermal processing to create some new texture or while retaining the nutrients. Other parts of the quinoa, especially leaves, are much underutilized. So you can make vegetables out of these leaves, not a problem, especially the young leaves. Freeze-thaw stability, even though we started them under the laboratory conditions, it has never been much utilized for commercial applications. So that can be explored for frozen or even canned food. In the first part of the talk, we look at these saponins in quinoa. They are bitter, so we want to get rid of them. But saponins has already, as I mentioned, has biological activities such as anti-cancer. In fact, in many traditional medicines, the traditional herbs that has been utilized for centuries or thousands of years, those herbs, medicinal herbs, some of them contains a significant amount of saponins. Similarly, quinoa also has saponins, so you may want to utilize it. And also the quinoa starch is really small in the granule size, so we can utilize it for controlled release and delivery of nutrients such as bioactive components. We have already done some of the work on that aspects because of the limitations in space and the time. Today, I'm not going to touch upon that aspects. This is some of the references we have consulted. Thank you. I would like to thank the Universitas Diponegoro and also the Faculty of Medicine for inviting me to come here and to give a talk. Thank the organizing committee of this conference. Special thanks to Professor Diana for inviting me here on a personal level. And also thank Emma for the chairing of the session.
Thank you very much. Give applause to Professor Fan Zhu. Professor Fan Zhu, I will invite you to sit here with me to hear the questions, and we will get the discussion session now. Maybe from the audience offline, do you have any question?